Let me explain one more important thing. We are going to take input, right? Echo input from ultrasonic sensor using GPIO. So you can replace this switch with ultrasonic echo input. If you remember. Anyway, let me first talk about this GPIO switch. Let me draw a timing diagram of this switch. Right? If you push up or down, okay, let me draw the status of this line. Okay? You push up or down the switch, or close the switch or open the switch. Right? Push up or down. Right? Push up, then waveform. Let me go here. Distributor. So you push up, then switch time. Then the human, right? You push up or down. Then duration is like, I don't know, is like how long? It would be 1 millisecond. I don't know. Push up or down. Very fast. I don't know. 10 milliseconds. 100 milliseconds. Push up or down. Probably 100 milliseconds. Because human, right? We are so slow. 0.1 second. Right? Push up or down. Right? Then that is a line, status of that line. Then how about this line? That is interrupt input. No blue. So let me use sample. Okay. The line of this interrupt line. If you push up, right, you push up the switch. Push up the switch and push it down. Right? Down the switch. Then interrupt line would be this line. Two. One. So it goes up. Right? Upwards. Goes up. Then what would happen? Right. Stays high, right? Stays high. Until you do what? This interrupt line. Stays high until you do clear the bit, right? Clear the status bit, right? You have status register. Yes. You push up the switch, then status bit will reset to no one. Okay? So that this line is just reflecting the status bit. So it will be stay high until you clear that bit to 0. Okay? So using software, using the program, okay? The program in interrupt service routine. Remember the two things you have to do in ISR. In ISR, you have to do two things. At the end, right? At the end of ISR, you have to write to end of interrupt register. Here. EOIR, end of interrupt register. So the ID is 61. You have to write 61. Then you are informing, okay, you are informing GIC, okay, I'm done processing it. And one more thing, you have to clear that bit. So before writing to EOIR, you have to notify, let's say, notify to GPIO. That's that corresponding, IO. You have to notify GPIO, okay, I'm done. By clearing that bit to 0. Okay, then the two, this line will go down. Okay, and then it stays low. Then you push down the switch, and it goes up again. Because that status will be the event, right? Push up event, push down event, right? So that status is again will be set to 1. Set to 1 again. This point, right? This point. Then same thing. You have to clear that bit, right? Software is clearing that bit. Then line goes down, right? Software should clear that bit. Then it stays. It goes down. Does it make sense? So two events happens when you push up. One event, right? Interrupt, and another. Okay. Then last time when I show you a demo, right? If I don't clear that bit, okay, you push up the switch, then the interrupt line goes up. Right? If you don't clear the line, then 2 prime will be 2 prime. Same line in the other case. You don't clear this bit with the software, then it keeps a circuit forever. Keeps a circuit forever, right? Then what is the implication? What is the implication if you go to this? To GPIO, to your distributor, GIC, generic interrupt controller. So in the office, right? I showed you a demo, right? If you don't clear the line, then interrupt is generated continuously because GIC sees this level. It is by default it is set to level sensitive. Level triggered or level sensitive interrupt. So as long as this line is high, level sensitive or level triggered means as long as this line is high, then GIC think of it as interrupt occurrence. Okay, so that means what? That means in ISR you come back, right? By writing to EOIR, right? You come back to the interrupted program, right? Then another interrupt is generated because the line is still high. So that means your CPU jump into same ISR and come back, but the line is still high. So you come back to this ISR and do this, keeps doing this operation forever. Does it make sense? So GIC is providing, one more option: level sensitive or edge sensitive. Edge sensitive trigger operation. That means if you change that configuration, number 61 interrupt. Instead of using level sensitive, I want to use edge sensitive. That means edge, right? So this line goes up this edge, and GIC think of it as interrupt occurrence. So the thing is, if you change the setting in the distributor, I did some experimentation. This one, GICD configuration register. Okay, let me show you the PowerPoint. Distributor, right? Distributor. This one, configuration register. If you change that the setting in the configuration register to interface. Okay, so distributor. Okay, so here set each IO interrupt to level or edge sensitive using configuration register. Okay, so you can check out the data sheet. Distributor, right? Distributor registers. Configuration, right? Interrupt configuration register. So using this 2-bit is allocated for each interrupt source. So number 0 interrupt, ID number 0 2-bit, ID number 1 2-bit, okay, ID number 61 2-bit, 2-bit, right? So 2-bit register, 2-bit, right? So here 2-bit. So first configuration register, the first 2-bit is for ID number 0. The last 2-bit is ID number 15, 15, right? So if you do the math, then to set configuration for 61, which register you have to touch? 0 register, 0, 15, right? Next 15, 1, next 15, 2, next 15, sorry, next 16, sorry, next 16, 3. So you have to touch configuration register number 3 for ID number 61. And you have to do 26-bit, shift left to find out the corresponding 2-bit. Okay. So, I changed that configuration to 10. 10 means edge sensitive. Okay. So I did some experimentation. So if you change that to edge sensitive, if you don't clear this bit, you do not clear this bit in ISR, then interrupt is not generated again. Only one time generation when you push up. Even though you push down, no interrupt generation because status register still contains that. You didn't clear that bit. Okay. So this line is fluctuating, like goes up and down. This line goes up and this line goes down, but interrupt line from GPIO stays high even if you don't clear. Okay. So same thing will be happening in ultrasonic case because in ultrasonic example sensor we are going to use the GPIO. Same GPIO. Okay. So GPIO is generating a trigger output. Trigger. So remember that trigger, right? You are generating this pulse, the trigger, and in response, right? In response, you are getting echo input. You are getting echo input. Ultrasonic sensor. So echo input is like 1. It's number 1, right? Push up and down. Right? So echo input, right? The echo. In this case, 38 millisecond duration. Switch up and you push down. So it is like the waveform looks like this. And interrupt will be generated this time, and also this time, 2 times. Okay. And you have to make sure, you have to make sure clearly. This set to level 2. And also it's anyway, you have to make sure you clear. Any question about this? Does it make sense? 지성, what do you think? 그렇죠? 기원, what do you think? 그렇죠? So okay, so by default setting, by default, the issue is in ISR you have to clear that bit. Then things would be working fine. Whether you set this interrupt to be level 3 or edge sensitive, edge trigger. But what I want to explain is if you don't clear that bit, what would happen in edge level trigger and edge trigger? Level trigger case, interrupt will be continuously generated. GIC recognize that high level as an interrupt. So interrupt will be generated continuously. But you set it to edge trigger, then one-time generation. If you don't clear that bit, but you have to follow the protocol. Protocol is clear that bit. Clear 2 times, right? 2 places. End of interrupt register, okay, program, and status register. You have to import 2 places. GIC interrupt controller, I'm done, and the IO device, which generated that generated interrupt. The 2 places, there is 2 obvious, right? You have to you generated interrupt, then I'm telling you I'm done. There is obvious protocol, right? By writing something. So writing data. So any question about this? Okay. So then let's talk about ultrasonic, right? I want to show you a demo. So again, ultrasonic sensor operation, super simple, right? Again, super simple. So using GPIO, we are going to generate this trigger output, and trigger output is connected to pin 1, pin number 2, right? So you're providing that short pulse to ultrasonic sensor, and this pulse sensor will generate this ultrasonic signal. This 40 kilohertz ultrasonic signal using this T transmitter T marking, right, and receiver, right? So using this transmitter, it is generating those pulses, series of pulses. Then that is reflected by these obstacles and coming back to the receiver. So you want to measure the round trip time, right? Round trip from here to this time, round trip time, round trip. Not one way. Okay? You go and come back. You go this way, you come back. Right? So this pulse width, this echo pulse width is equivalent, is equal to that round trip time. The echo input, right? So this pulse, this travel is equal to this travel time. Then how fast ultrasonic signal is traveling? Same as sound, right? 340 meters per second. Every second, ultrasonic signal travels 340 meters, 340 meters. So using with that in mind, we can do simple calculation, computation to measure the distance, right? If let's say it is echo, this one is echo input. This one is echo. Let's say this one is 100 millisecond, right? Then 100 millisecond, right? 1 second, 340 meters. Then 100 millisecond, it can travel 34 meters, right? But that is round trip time, right? So the actual distance, you have to divide the number by 2. So 70 meters. Right? So from sensor to the obstacle. So simple math. Right? So once you know the duration, then you know the distance. Right? So simple, very simple operation. So let me show you how their block diagram I'm providing. This one, Vivado design example. Okay, you open up this the reference design. And design is actually very simple. GPIO. Okay, so here you have PS, processing system, PS, ARM CPU, and we have a bunch of GPIOs, right? So first, this one is connected to LED, okay, and this one is connected to switches, right, and buttons, and the GPIO on top. That, but if you click on this. This one is taking input, echo input. Okay. So there is an 8-bit register. You can use just one bit. Okay. Okay, 1 bit, because the echo is 1 bit, 1 bit input. But I open up this 8-bit, port, so you can use any 1 bit from this 8-bit, right? This 8-bit, right? Echo. And output, this one trigger, output, right? Same thing goes to trigger. So I open up 8-bit output port, okay, trigger, but you can use just one bit, right? LSB, for example, right? So 2 GPIO devices, and you have to make sure that is connected to where? That is connected to this P mode. So this one, I think this one is a trigger. Okay, see the connection? 2 connections, right? The 1 bit. This one is trigger output, and this one is echo input. This green is echo input, and blue is trigger output. Okay, so I did make connections. Then you have to make sure, right? The constraint file, you have to map, right? Trigger pin is connected to this Z port, right? This the zinc pins. Echo is connected to this W. Okay, so that is important information. Then the final thing you have to check is memory map, right? Switch is mapped to, switch is allocated from this base to that location, 41 to 1, and trigger 41 to 4. Okay, so you have to check out memory map to write program, right? And echo is 41 to 3. But echo case you don't have to, right? Echo case you should, because you have to clear that bit, the status bit. So there is enough information, right? Then program, right? Program is switch next to ultrasonic. Very similar to GPIO project, right? That you switch up and down project, right? So here, so echo, check out this header file. Then for trigger, right? GPIO 41 to 4, and echo GPIO 4 echo 41 to 3, right? So from here, I'm because echo, right? I'm enabling interrupt here. So in GPIO, right? So we are using two separate GPIOs, right? GPIO, one GPIO for trigger out, and another second GPIO for echo input, right? So for echo input, you have to enable interrupt. Because echo, right? You enable interrupt. Then then routine, the initialization, right? Database setup, interrupt enable, and GIC setup, generic interrupt controller, right? And we are using number 61, same 61 ID, right? This ID distributor, right? That is coming in through this ID number 61. We are using 61. So you have to set ID number 61 related registers in GIC. GIC, 61 priority, 61 target, right? Number 61 enable, right? 61 related registers set up. So to refresh your memory, the first one is distributor enable, global enable. You want to make that distributor that is whole hardware effective, right? Whole hardware, right? And then individual interrupt enable, interrupt individual IO device enable, right? So you have to touch enable number 1 register, number 0 and number 1, because each enable register contains 32-bit. Register size 32-bit, right? So 32 enables, right? ID number 0 to 31, and ID number 32 to 63. So number 1. So this one, okay. Then target register. So we have CPU 0 enabled, only one CPU enabled. So you have to forward that interrupt to CPU 0. What's 1, right? So CPU 0, body setting 0, 1. 0, 1 is binary. What is binary number? 7 zeros and 1. That means your CPU 0. Okay. Then priority, I set it to 1, 0. Okay. Priority for ID number 61. Okay. And that is about distributor setting. Then CPU interface setting. Okay. CPU interface module enable. Then threshold setting, priority mask register. Here, PMR. Right? Priority mask register. Here you set threshold. Right? If the incoming interrupt priority is higher than this threshold, that will be forwarded to your CPU. Priority based, right? Obvious mechanism. And then it is jumping to C program, main hello, right? So what is that? This program is simply very simple, right? Main hello, right? This is a while loop, just while. Right? So you can ignore just this bit. You're continuously executing this while loop, never exit, right? So it is generating trigger output, right? So I did some experimentation. If you set this loop count to 900, then that is roughly 1 microsecond. Roughly 1 microsecond, right? So that 1 microsecond. Right? Sorry, 10 microsecond. Sorry, 10 microsecond. I think. So you have to make sure you are generating, that pulse. So yeah, I should comment on this. Okay, I should change that 10. Okay? So then look at this. So 0 at the beginning. 0, draw, the timing diagram in your head, right, in your brain, right? 0, and then 1 goes up, then some loop count, right? It stays high, then it goes down, right? It goes down, and it goes down, enough time. enough time to get echo input. You are expecting echo input, right? So we have to wait until echo input comes in. So that is enough time, I think. Okay, you can do some adjustment, right? Group count, and go back to while loop. You continuously generating trigger output 10 microsecond pulse, the pulse train, right? Pulse train. Any question before showing you a demo? I need to go to my office. Any question? Too clear? Explanation too clear. Nothing to ask. Okay, so let me go to my office and show you that. Okay. Come on. Okay, can you hear me? Someone. Okay. Okay, so let me show you a demo. So here I have an ultrasonic sensor. I have an ultrasonic sensor here. Okay. I'm not sure if you can see this. So that is obstacle, right? I'm going to this obstacle will be moving closer to the sensor, and I'm going to move it, farther, move it away from the sensor like this. Okay. And let me show you this logic analyzer input, logic analyzer monitoring output. 32 1 millisecond sampling rate, and I want to collect. I want to collect 10 million samples. That means what? That means 10 second. Okay, hold on. Okay. Okay, so this one is like 10-second worth time, right? 1 million sampling rate, and I want to take 10 million samples. Okay, this one would be useful. Okay, then I need to okay, turn on the board. I already did that. Okay, turn on the board. Then okay, this one is the program we are going to execute, right? One thing I forgot to mention. One thing I forgot to mention in ISR, what you are doing in ISR, the same operation. I'm toggling LED. Toggling LED. That means what? That means okay. Let me explain that in the office. In the office. Okay. So first, let me show you the demo. Then go back to the office. Okay. So download it to PGA. App and debug. Okay, then to big. Okay. Okay, then execute the program one by one, instruction by instruction by pressing F5. Then enable stack setup and routine vbar setting. Then distributor configuration. Okay, enable target. Okay, CPU 0 is target. Priority 10 for ID number 61 and CPU interface setup, right? So enable and threshold setup to the lowest. So I can't. I'm going to take any interrupt you are sending me, right? Then you know what? The C function call, right? Branch and link. So that point. Okay, let me then now press F8. Then CPU will continuously executing this file loop, right? So let me press F8. F8. Then something is happening. So actually, I'm not sure if you can see this blinking, toggling, this toggling, or LED toggle, LED toggling. But LED toggles because it is executing ISR, interrupt service routine, continuously toggle, right? So that means the interrupt is continuously generated because of the echo input, right? So let me then now position that into very closer to ultrasonic sensor. I'm going to move away. Right? This obstacle. Then before that, let me run this logic analyzer. Okay, 10 sec. I'm going to collect 10-second words. The signal, right? So run. Then I'm going to move. See? Okay, 10 seconds. So let's analyze this waveform together, right? This collected input, echo, and sorry, the trigger and echo, right? From the beginning. So at the beginning, so look at this. This one is D1, right? That is trigger output, right? So you can measure the time using this You can measure the time using this, right? So time is like 12, you see? 12 microsecond. Okay, trigger output roughly, roughly, I don't know, 10. So it works, right? And then the first echo input. So at this time, right? So the obstacle was very close to that sensor, right? So check out this 391 microsecond, right? 391 microsecond, right? So you can do some calculation. So what do you have to do? Let me open up that. Ultrasonic sensor and calculator. Okay. So what you can do is what? So you divide every microsecond. So according to that, travel time, every microsecond, the ultrasonic signal can travel this distance, right? So we got that number. So let me plug that number into that equation, right? 391 microsecond, right? So 391 divided by 2 because it is round trip time and multiplied by 0.034. So 6 centimeter. I think it was like 6 centimeter at the beginning, right? Something like that, right? And let me check out the last signal we collected. Last one. This is the last one, right? Okay. 0.7 millisecond, right? Or 695, right? 695.7, 695, right? So plug that. What do you have to do? Clear, right? 659 divided by 2 multiplied by 0.34. Did I do it correct? No, I don't think so. So more than 2 times, right? So let me collect it again. I don't know. Something is wrong. It's supposed to be some millisecond. So let me move it very further. Okay. So I don't know. It is hard to position the sensor vertically. So probably that is an issue. So let me do it again. From here to very far away, right? Very far, that far away. Okay. So let me do it again. So run it. I think it is more than 30 centimeter. Okay. So let me show you the last one. Something like a 1 millisecond, right? So 8, 15, 8:15 seems not that long. 8:15, is it 8:15? Okay. So 815 divided by 2 then multiplied by 0.34. What did I do wrong? Oh, okay, 13. Something is wrong, but you can do the math. I don't know. You can do the experimentation. Something is wrong. So it was, working very, fine, but I don't know what is wrong. But you can see the clear, difference between that echo, time. Okay. Okay. Let me go to the office. Let me go to the classroom. Then continue. Stop sharing. Stop sharing. Someone, that's it, right? Do I have to do some more? Is it okay? Can you share the screen? Host Conan. Host. Host. More. Make host. Yes. I see. Okay, I think the problem was the line. This line. Right? So I did something, and this line, right? It was this one. So this line is here. Right? This the wire. This wire is here. So that is why the difference is not that big. So if you remove this, then the clear difference. Let me okay. So let me show you. Let me show you clear difference. So if I run, okay, you can do that. Okay. Someone, can I go to the classroom? It's okay. 음? 예. 문제가 있어? 거기서 안 돼? 끝났는데? 이걸로 reclaim host 이렇게 되나? You are now host. 이거겠죠. 호스트냐? 오케이. 한번 해볼래 가서. 한번 해봐. 호스트. Okay, the demo was not that smooth because of that wire, right? I think. 고기를 꺼야 되는 내가. 웨스트가 되네. 거기서 줌을 꺼야 되나? 글쎄요. So LEDs are blinking, right? Four in the middle, that is blinking, right? Because inside ISR, the toggling is happening. And inside ISR, right? So that means that what ISR? You think of it as echo input, then ISR will be executed, right? ISR will be executed. Then so inside here you are toggling. Let me show you the code. In ISR, I'm toggling LED. That means what? That means depending on this time duration, right? Cool. You can see the difference in blinking, toggling, because the frequency is different. So that is that time is shorter, like I don't know. The time, look at this. The time object is not detected, then no object detected, then you are expecting 38 millisecond echo input, and otherwise you are getting the less duration, smaller duration than that 38 millisecond. Then you can do some reasoning. Right? So you are blinking LED, and so LED blinking frequency would be different because that time is different. The time is shorter sometimes. The time is longer. Then ISR is executing. ISR execution frequency is different depending on the distance. So the LED blinking speed will be different. It is actually visible. I did some experimentation like this. So LED blinking. These 4 LEDs are blinking, right? So that so the frequency is different. You can do measurement. Okay. Any question about this? Ultrasonic. And again, so when I did experimentation, there was a wire in the middle, and ultrasonic signal, got reflected by that wire. So that is why the distance was not that dramatic. But what I did, the last night, I did some experimentation, and what I observed is like this. This is what I collected. So here, when distance is short, then I got 773 microsecond echo duration, and distance is too long, very long, and I got this number, 1.8 millisecond. And you plug that number into the equation, 13 centimeter distance, and 30. So you can measure, you can do some measurement. Any question about ultrasonic? Too easy, too simple. Okay, that is about ultrasonic. Then I have one more thing to talk about interrupt. But we have 50 minutes left, and that is not enough time to discuss new topic. I want to talk about this software generated interrupt. Okay, so that is the last topic, and I need 1 whole hour to discuss about that. So we can finish a little early today. If you don't have any question. And when it comes to class project, okay, so the last thing, right? Class project, I'm asking you to use interrupt, right? Ultrasonic, right? Use interrupt from GPIO to check the distance, right? So you can use a timer. The reason is I ask you to do context switch every 1 millisecond. Right? Timer interrupt is generated every 1 millisecond. Right? Timer interrupt. Every time timer interrupt generated, you are supposed to do context switch. Task 1 to task 2, task 2 to task 3, 3 to 1. Round robin, right? And if you check the ultrasonic signal, echo signal duration, so object is not detected, then 38 milliseconds, right? So that is why I ask you to use interrupt instead of polling. Right? So you could use probably polling method. Keep checking using GPIO that echo signal, right? This echo signal is asserted. You can keep checking the status, line status using GPIO. Right? But you cannot wait. You cannot wait 38. You cannot keep holding. You cannot keep holding CPU for 38 milliseconds because context switching is happening. Task context switch is happening every 1 millisecond. Your operating system, right? So this is the one you are going to design. Right? Context switching happens every 1 millisecond, but to measure 38 milliseconds, you have to keep holding CPU for that time duration. So that doesn't make sense, right? So that is why I ask you to use timer interrupt. Right? So interrupt is generated. Think of it 38 milliseconds. Right? Interrupt is generated and check the time. Check the time using global timer program. Private timer is used for the tick generation. Task schedule. So using global timer at this time and use global timer at this time. Read global timer count data, read global timer count data, and do subtraction. Then you can the pulse width first time. That is one thing. Okay. The reason why I ask you to use interrupt for ultrasonic sensor. Okay. 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 That's it. That's it for today. Huh? Say it again. Task 2. So yes, you can design your software architecture. Right? So what is given to you is every 1 millisecond, context switch task scheduling should happen in round robin fashion. 0, 1, 2, 0, 1, 2, 0, 1, 2, that round robin fashion. Then how to collect and where to collect the time information, right? Global time information, Task 2 or in ISR, it's up to you. You design your software architecture yourself and give presentation. Okay, any other questions? Yes. Yes. What? One second. So every one second, you're supposed to print out message, right? So probably one time, one measurement every second. That would be okay. Because to human, right? 1 millisecond, 1 millisecond, 1 millisecond. Right? You are sending too many messages to your right? Then human cannot. It is scrolling up too fast. Right? That's why. And think about you are applying that ultrasonic sensor in self-driving car, and fishing application, and parking application. Right? You park your car, and you want to measure the distance. Your car and the wall, right? So then 1 millisecond is probably not, but this the toy example. 1 millisecond is 1 second is. Any other questions? Okay, that's it.